Welcome to Module 4. During this module, we will learn how to continue modifying our scripts to automate data processing. Today we will focus on incorporating loops and creating new functions. The learning objectives for today include discussing the structure and syntax of loops to iteratively run commands, employing a couple types of loops to segment data, converting codes into functions, and we will run through a data analysis workflow and streamline our data processing steps. The first type of loop I'd like to talk about are for loops. For loop executes a statement or a set of statements a set number of times. Here's the basic syntax. For some index, which will loop from a starting value by each increment, say 1 or 2, to an end value. And for each iteration, MATLAB will do something, and then end when you've reached the final value. You can also nest loops within each other using different counters, in this case, I and j. For example, say we have a data matrix from several subjects and several conditions. We can loop through that analysis first by examining each condition, the inner loop, and when this is done for the first subject, it will loop to the next and analyze each of those conditions for that second subject, and will continue until you've reached the total number of subjects. If loops use logical statements to define when MATLAB will execute a command or process. If the condition is met, MATLAB will do something. If you have more than one set of logical statements, you can add an else or else if. So, for example, if condition equals 1, do something. Else if condition equals 2, do something else. And else, meaning any other condition listed, do something else. Let's go through one example that uses a combination of for and if loops. I have a following matrix of data. Data 1 looks like this. The first column is a grouping identification, the second column is the subject ID, and the third column is the mean performance. Before we create our new data matrices, let's pre-allocate matrices with NANs equal to the original size of our data set. That way, when we subset our data set into group 1 and group 2, we will have an appropriate number of rows and columns. Now let's look at the codes for the loop, which will subset our data into group 1 and group 2. So what I'm doing is I'm looping through our original data set 1, looking at each row. So this size command, which we've used before, is now going to indicate the number of rows in data set 1. And now it'll go row by row until the end of the data set. The first thing it will do is it will look within the first row and the first column and see if that value is equal to 1. And if that condition is met, it will put that data into group 1. Otherwise, it'll put that data into group 2. And it will continue looping until the end of the matrix. Here we now have two additional data sets. Data 1 G1 for group 1 and data 1 G2 for group 2. NANs are now placeholders for the positions in which we had data from group 1 in the dataset for group 2. What would happen if our data matrix had data from 3 groups instead of 2? In this case, the if statement, as written, would put data from both groups 2 and 3 into data 1 group 2. Obviously, this is incorrect. We would need to add an else statement modifying this loop. Switch expressions are similar to if statements and take the following form. Switch, some expression, and the value of that expression is listed as cases. So if expression is equal to value 1 in the first case, it will run a set of commands. If it's equal to value 2, it will run the second set of commands, and then will end. Now let's go through the previous example and reformat it so that it's a switch expression. Again, in both cases, the for loop will go through all rows of data from the original dataset, starting with the first row and going to the last. The switch expression defines a statement or value. So here, it pulls the value for data 1, for row defined here, and for the first column. If the data for that row is equal to 1, meaning that it's for group 1, then those data will be added to a new data matrix. If data 1 for that row is equal to 2, then data will be added to a separate matrix. Again, what would happen if our data matrix had data from 3 groups instead of 2? In the switch example, nothing would happen to data from group 3 because we have not specified any cases that are equal to 3. Each case has to match exactly. If we wanted to subset data from group 3, we would have to add another case. Before moving on, there are other loops that you can use. Here I'm only talking about for, if, and switch loops. If you want to learn more, search the documentation for other types of loops. We've already created several scripts and have briefly talked about the benefits of writing scripts compared to typing out commands straight into the command window. Obviously, the pros of using scripts is that you can save your M files, you can edit your M files, and you can comment out your M files using a % symbol. There are a few cons that I want to reiterate. All of the operations in a script you run result in new variables in the workspace, which can clutter up your workspace and take up memory. Second, codes are hard-coded, so you have to do a bit of code editing to run similar commands on similarly structured data sets. So you can't simply provide an input argument and an output argument. You have to actually modify each line of code. Functions allow us to simply take an input, do something with that input, and only output variables of interest, rather than all outputs, including variables created in intermediate steps. The resulting scripts that call these functions are streamlined, and that way the opportunity for error is reduced because you have less codes to modify. However, writing scripts can be less than intuitive for new programmers, and luckily MATLAB helps with this. Let's try to adapt some codes that were written for Module 3 practice problems, and create a function that computes the mean and standard deviation, and replaces data that are outliers with NaNs. Let's create a vector of random numbers that has 50 rows and 1 column. And then let's calculate the mean and standard deviation and index the outliers within that data and set those data equal to NaNs. Let's think of what we need to do to create our function. First, we need to create 4 sets of outputs: the mean of our data set, standard deviation of our data set, the number of outliers, and say data without outliers. We also need 2 inputs, our data matrix and our outlier criteria. By adding this value for how many standard deviations from the mean, we can see the effect of changing the degree of outlierness. In the editor window, we can create a new function, which MATLAB sets us up to fill in. First, we should change the name of this function. Let's call it outliers. Note that there are functions within the stats toolbox that also do more elaborate versions of an outlier analysis, but let's say that we had no idea about these functions. The first thing to do is copy our set of codes and look where we can make things more generalizable. So far, this is all pretty straightforward, but now we want to modify the number of standard deviations away from the mean. Let's call this variable outsize. And now let's add that as an input argument. So we'll have our first input as data1, and our next input argument as outsize. And now we've just added outsize and replaced our previous 1.5 standard deviations with this variable. The last thing I want to do is I want to add some codes that allow us to count how many outliers there are in our data set. Let's call this numout. And we're going to set that equal to the length of our outliers, which are the number of indices for our outliers. Now we want to make sure that we have all of our output arguments designated. These have to match exactly to what's in our function. We want the mean and we want the standard deviation. We also want the number of outliers and the final data set with NaNs replacing those outliers. Notice that I've deleted one variable from the workspace, the outliers indices, since we don't really need them, and we can see within our new data set those values are replaced by NaNs. And when we go to save this, MATLAB would automatically save this file as the name in the first line of our function code. I'm not going to save that here because I'm going to show you what the final function will look like once I've added additional details in the comments section. So here's the example of the final outliers function. We have our input values of data and outsize, and we have our mean data, standard deviation, the number of outliers, and our final data set with the outliers identified as NaNs. I've provided additional comments to say what this does, and details about the inputs and outputs that are necessary. Now what's nice is that I can do the same analysis on outliers with a new dataset. I'm going to create dataset 2, which is another set of random numbers, but I could have done this on any size. So say, let's do 100 values. I'm going to call this function using our dataset 2 and a threshold for our standard deviation of 2.5. I'm going to request the output to be called mean data 2, standard deviation data 2 outliers, and data 2 no out, meaning that no outliers are in that data set. Data 2 no out should have NANs greater than 2 standard deviations from the mean identified as outliers. Here we have none. But if I wanted to rerun that code in the same way, and now look for a threshold of 1.5 standard deviations, I'll see now that some of those data were replaced by NANs. So let's put all of these ideas into practice by employing some codes that we have already created to call functions that input data, downsample data, compute means for segments of data, and create new figures to visualize these data. First, we will use the import file function that we created previously to import the EEG data from 5 subjects from 2 conditions. Notice how quickly we were able to import our data, rather than using the built-in toolbox for data import. Now, let's subset the data by condition. Recall that our previous script did the following. Let's convert these lines of code into a simple function called subset condition, which will allow us to subset our data into condition 1, condition 2, or both. Before we copy and paste our codes into a new window, let's take a look quickly at some of the warnings that MATLAB is giving us. MATLAB says, if subject 1 is an indexed variable, performance can be improved using logical indexing instead of find. So we're going to try and do this and incorporate this into our new function. Let's first copy our code into a new function editor. Now let's replace this find command to just use our logical operators. We can do this by simply stating this. Now, any data that meets the condition subject 1 condition equals 1 will be put into a new data matrix called sub1c1, and the same thing for condition 2. But I want to be able to select whether or not I want to subset condition 1, condition 2, or both. Let's add an input argument. So in addition to sub1, we also want to include a new variable called numConditions. This will allow us to create an if statement for each of the number of conditions. If number of conditions equals 1, meaning I only want to subset data from the first condition, I can do this. And then I can write an else statement to do this. And now I have a third statement where if I want to do both conditions, the number of conditions will equal 3. Now let's take a look at the finalized codes with all of the details added. Here I have some additional comments that suggest that data should be a data table with a condition variable, and the number of conditions equal to 1 is condition 1, 2 is condition 2, and 3 is both. Now let's call this function. Here I've added the 3 option to do both conditions. And now what I see in my workspace is subject 1 condition 1, subject 1 condition 2, and so forth for all subjects. Now let's downsample our data or reduce the number of sample points so that we can reduce the size of our data matrices. Often, the sampling rate for neuroimaging data like EEG and MEG is way higher than what's necessary to do some basic time and frequency analyses. Note that because we have the signal processing toolbox installed, there is also a function called downsample. Let's pretend that we don't have this toolbox and create some codes that will allow us to do something similar. It's important to note that since we are no longer working with a sampling rate that's an even integer of 500 or 1,000, for example, we need to be careful about downsampling, because any values that are not a power of 2 will result in incomplete data at the end of the file. Right now, our sampling rate is 512. So we should also create a time variable that creates a timestamp that runs the length of the total dataset. Also keep in mind that in addition to downsampling our data, we need to downsample our time variable so that we have a time value that corresponds to our data. That way, if we plot our data, we have the correct time interval. If our starting sampling rate is 512 and we downsample by 2, we have a new effective downsampling rate of 256 samples per second. To do the downsampling, what I've done now is I've looked at subject 1, condition 1. I've gone from the first row by 2s to the last row for all columns. And I've done the same thing for the time sample. If I want to downsample by 4, giving us a sampling rate of 128 samples per second, I would do the following. I would just change the increment with which we're sampling. And I would do this both for subject 1 and for the time. Let's create a function called dsby that does a similar downsampling, but allows us to input any value of interest to downsample by. For the sake of time, I'm going to show you the finalized function. Here as input, I have my data, my time vector, and the downsampling value. And the output is the data downsampled and the time downsampled. And all I've done here is added this variable ds as my interval for which I'm going to step through the data. So now I'm going to call this function, and I'm downsampling by 4, giving us an effective sampling rate of 128 points. Recall that our effective sampling rate is now 128 samples per second. So to determine how many samples are in the first half of a second, we multiply 0.5 seconds by 128 samples per second, giving us 64 samples. For the practice problem from Module 3, you wrote code that may have looked something similar to this. It takes a data matrix called mean C1 as an output, and as an input, you take the values for subject 1, condition 1 for C3, and computes a NaN mean for each different interval. Let's rewrite this into a loop. We know that we need to split up our time series into 4 segments of 64 samples. So section 1 would range from row 1 to 64, section 2 would range from 65 to 128, section 3, 129 to 192, and section 4 from 193 to 256. To make this code more generalizable, we can think about it in the following way. Let's first start with our end value. Our end value is simply 64 times whatever segment we're using. So 64 times 1, 64 times 2, 64 times 3, and 64 times 4. To get the index for the first value, it takes a little bit more thinking. Here I have a simple equation that allows us to go step by step through each of those different segments, making sure that each of the segment lengths are still equal to 64 points. You can take a little while to think about how I arrived at this conclusion. Now I can create a loop that goes from 1 to 4 segments. For each of those segments, it'll create a new row vector with the mean for subject 1, condition 1 for the downsample data for electrode C3. And it'll loop through to compute those means and standard deviations in this way. If we look at mean of C1, we'll find 4 values for subject 1 corresponding to the 4 time segments. Just to make sure that this is correct, I want to test this against the actual indices that I know are in fact correct. When I look at my test case, I see that the values are identical to the values I computed using the loop. So now I can copy and paste these codes and modify them for each of the subsequent subjects. Here I've modified the code, updating the subject ID number. And I can run this code, updating this mean C1 value for each of those subjects. Here we now see data from subject 1, 2, 3, 4, and 5 for segments 1, 2, 3, and 4. Now what I'd like to do is plot the means for each of these time segments for each subject. Before we start, let's take a look at the bar graph function and the documentation for this function. Here we see the basic syntax for the bar graph function. Bar of y, or some matrix, creates a bar graph with one bar for each element in y. If y is a matrix, then bar groups the bars according to the rows in y. So this is exactly what I'd like to do. I've created some sample code that creates this figure, adding an x and y label, title, and a legend. Here's what this figure looks like. Each of the different colors represents a different subject, and along the x-axis we have our time segments, and along the y-axis we have our mean EEG amplitude. So we get a very good idea of what our data look like. We can also see that subject 1 has a very different profile than the other subjects. So as we add more subjects, we can plot our data in this way and determine whether or not we have one subject that might be behaving very differently than the others. To recap, we learned about the structure of different loops and wrote several functions that use loops to automate our data processing and reduce the total number of lines and opportunities for errors. In our workflow, we took raw data, we subset it, we downsampled it, we computed means, and we plotted those results. Taken together, we have created a data processing stream which has a reduced number of lines of codes and is able to replicate in an automated way. Thank you very much for your participation in this workshop. Please check the website for the answers for the questions and answers from students and any supplementary problem sets that were completed during the lab sessions.